Good morning, everyone. My name is Dinil Mon Divakaran, and this work is with three other co-authors, Kawai, Hiro, and Wrestling. We are from the A-Star Institute for Infocom Research. As has been introduced, the work is on evidence gathering for network security and forensics. So I think one of the important takeaways from yesterday's dinner talk was that don't rely too much on single evidence, right? So the premise is similar. We are trying to figure out if we can say something more with more number of evidences. Right? Before I start, I also would like to say that this work actually borders between security and forensic, and it's kind of similar in many network security and forensic work that at least I'm involved in the sense that the solution can be used for forensic analysis, it can also be used for security analysis, offline, online, and real-time would be the challenging part. So, so let's start. I'll start with the context and the problem, describing the objective, and give you an overview of the evidence gathering framework. Okay. The core of the framework is a modeling and analysis component, and we use regression for carrying out that part. Besides the modeling and analysis, or beyond that, what we do is correlation and a meta decision-making system. We develop a meta decision-making system, and all this is evaluated on real data set that we obtain from that's openly available. So the context of the problem is that there's always a need to detect anomalies in a network, and anomalies can come not only due to security-related incidents, but also due to faults in network. So you can have anomalies due to mismanagement configuration as well. But what we're interested here in is a set of anomalies that are related to attacks. Okay. So when we talk to operators of enterprise networks, like those that use SIEM, the security incident and event management system, one of the problems they have is that they get a lot of alerts, they get a lot of alarms, and they're quite huge depending on the size of the enterprise network, and many of them are false. So you need to analyze them in detail to understand whether they're true or false. So we look into that context of saying, okay, there are anomalies, but can you say more that some of the anomalies are related, they are more important and they're more relevant, and others are not, or others are irrelevant, and you can see that they don't make much of sense. So that's pretty much what we're trying to do here. We want to detect patterns that can be related to anomalies. That said, anomaly detection in itself is a very old problem in the network community, and people have applied different knowledge systems or scientific tools such as expert system information theory, data mining, signal processing, statistical analysis, and so on. However, most solutions have been targeted to detect a particular kind of attack or particular set of anomalies, which means they're kind of dedicated. So you can't, for a user of an enterprise network, it's difficult to have all such solutions together. You want something which is more generic that can detect patterns than saying you want to detect a particular attack. That's what we're looking into. And the other is to bring the context. So if you see a network scan, a port scan itself is not a problem. It might be a problem when you have a related attempt to do, for example, a buffer overflow attack, right? The system we develop is to detect what we call these fundamental patterns, and I call this as evidences, though I think it's not the most perfect term to be used, but it's basically patterns that you feel are suspicious, but in itself you might not want to look into it and say that, hey, there's some problem with this pattern and we need to dig further, as in do it manually. So you want to collect them together and view it, analyze it, and then come up with a conclusion. So this is the objective of the work. When you detect evidences, that is patterns related to attacks and anomalies, analyze and correlate them, and the aim is to detect anomaly without the need to learn model from normal traffic. So again, this is a distinction from many works, that we are not doing the traditional machine learning where we learn models, machine models from normal data. So one of the challenges is that the community is facing is that you can't really get very clean real data, and even if you get it for one time period, you need to keep renewing it because the traffic changes dynamically over time. So that's kind of challenging to always have models that learn from normal traffic, that learn from attack traffic. So you need to always update your models. You need to have real data corresponding to these two sets. So to overcome that, we are not having a model based on normal traffic. We are looking into patterns that might be common for many attacks. So this is the overview of the evidence gathering framework. In the first stage, we develop a model. We do modeling of patterns, analyze and detect such patterns. In the second stage, we detect scans and illegitimate TCP sequences. So I'll come to what I mean by illegitimate TCP sequences. So this is kind of deterministic, or this is really deterministic. There's no probabilistic sensor. However, the model is probabilistic. Right? And the third one combines these two to find correlations and make decisions. Before I proceed, I also would like to tell you that you may feel free to interrupt and ask questions if it's not clear, so we don't have to wait to the end of the talk. So the first stage is on modeling and analyzing. Before we go into that, we need to know what are flows and sessions. These are commonly used terminologies in networks. So a flow is a set of packets localized in time with the same set of usually 5 tuple of source and destination IP addresses, source and destination ports, and protocol. Session is basically again a group of flows that you want to analyze together. Maybe it's like a number of SSH atoms to a port, so it's multiple flows, but it's a single session. So session definition is kind of variable. You might want to look at a destination-based session, which is like you have flows coming to your server, and that you might want to segregate based on session, saying that it's probably this port or the port and a source address. So you have a session between two end hosts and different sessions between different end host pairs. The traffic is represented by features, and there are numerous features that can be used on network traffic. For example, you can use flow rate, flow volume, etc. And in fact, you can come up with a few tens and even hundreds of features from packets and flows. For the purpose of demonstration, we look into only these 3 features. So one is the interarrival time between flows in a session. So you take a session and look at the interarrival times of flows. So flow it roughly translates to connection. So if you look at a bot, the bot might be trying to communicate to different servers at regular intervals. Right? So the interarrival time might not be so random as opposed to a human behavior, browsing behavior. This is not just applicable to HTTP traffic, but could also be applicable to DNS traffic, where if the marker has a DGA, the domain generation algorithms, which try to communicate, try to resolve different domain names, then might have some interesting patterns in the interarrival time. The other features are the size of flows. Size of flows can be analyzed in packets or in bytes, and finally degree of an enclosure, that is the number of distinct machines, a particular number of distinct machines an enclosure communicates to. So that will tell you whether it's in the normal range or not. Again, this is not an absolute measurement, that's relative, because if you have a network of 10 machines, you would have a degree going in the range of maybe 10 or 50 every few minutes. But if you have a large network, it can increase by an order of magnitude. So as I said, we use regression for modeling and analysis. These are 4 example patterns, and these are the 4 type of patterns that we detect using our system. So we'll explain. These patterns were obtained from real traffic from Mavi data set. So Mavi is a consortium from Japan, a consortium of different ISPs, so they keep uploading daily traces, and these are some of the anomalies in the traffic. So this is an example. The first one is an example of an outlier where one point stands out. So this count here is, I've kept it general, but it could be a number of IP addresses you're communicating to, for example. So this is an outlier, example of an outlier. This is an example of a perfect fit, as in your values at different times. So these are the time. The x-axis is the time. So at different time instances, you have almost the same count coming. So this count again can be the number of hosts you're communicating to. It could also be the number of packets in your flow, right? And the third example is of a linear increase. A linear increase can come if an attacker is trying to beat a system that uses a linear model to detect. So there's a linear model that sees if the increase is linear with respect to any feature, and if a system is built on that, then of course this can be detected, but a quadratic one or an exponential one cannot be detected. And a linear relationship can also come if you have something like a TCP SYN flooding attack, where for each SYN you get, the number of SYNACT that goes out during a TCP SYN flooding attack is always increasing, because the SYN comes from a spoofed IP address. So because the SYN comes from spoofed IP addresses, the ACKs do not reach the destination, so the victim is sending the ACK. So retransmission of ACKs happen, and therefore if you take the difference of this, you will see an increase. The entire modeling here is based on, mostly based on linear regression. That is, we assume a first order linear model, basically a model of a line. So you have an intercept, y is the observed value, which could be the number of packets in your flow, for example, and x is the discrete time points. So beta 0 is the intercept and beta 1 is the slope, and epsilon is the error in modeling. And usually in linear models you assume it follows a normal distribution, which means it's a zero normal distribution with a zero mean and a standard variation of sigma. Now what you do with the model is you try to estimate what your response variable is. That is, before you get the actual data, you try to figure out what might be the next value that you're expecting for the feature. If it's the number of enclosures you're communicating to, or the number of packets in a flow, whatever it is. So you model it, you try to estimate it. So when you estimate, you have to find the values of, you have to estimate beta 0 and beta 1, so we have the cap to indicate it's an estimate. And in least square method, which is the most commonly used method for line fitting, the coefficients are obtained as by solving the simple equation, which is you minimize the sum of the squares of the difference between the estimate and observed value. So y hat is the predicted value and y is the observed value. So it tells you the error. the error in what your model predicted and what is the actual value. And the estimates for the slope and the intercept are made by minimizing this sum of square errors. With this, now we can look into 4 different methods for detecting the 4 different patterns that we saw earlier. So the first one is you want to find outliers. So unfortunately, the least square regression method is very sensitive to outliers. It has a breakdown point of 1 over n, which means that you just need 1 out of n samples to be an outlier for the estimator to move away arbitrarily from the observed value. Which means your estimator can really be out of the optimal region or the correct region if there is at least 1 outlier, and theoretically, asymptotically, it's even 0, so you don't need an outlier. In the community anyway, there are a number of robust regression methods, and Thielsen estimator is one of them, which has a high breakdown point, and the point is close to 30%, which means even if you have 30% outliers, you can still fit the line almost correctly, right? And in Thielsen method, the slope is estimated as the median of all slopes. So if you have this XY pairs for a line, so let's say you have 20 points, so you take the slope of all of them and take the median, and that's how you get the Thielsen's estimation for these parameters. So given this, our hypothesis for detecting an outlier is as such, which means it's an outlier as long as the difference in the estimated value, so remember Ri is the difference between the observed and the predicted estimated value. So if the difference is less than the contact, a particular contact value, and if you take this, so you know it's around 30% is the maximum outliers the Thielsen estimator can tolerate. So if anything is less than 70%, then you can say it's an indianal, and is greater than 70%, you can say it's an outlier. That's a safe bet, but of course you can have a parameter kappa to say if you want to play with it, right? The second one is the goodness of fit. So we saw the straight line, and we want to know whether such straight lines are there in observed network traffic. If you have perfect fit, it actually gives you a functional relationship. A functional relationship is not common in network because there is a human often behind the computer, and what is expected is a statistical relationship. It's not a functional relationship. So the way you can detect that is by testing whether the sum of you can actually check whether the slope is 0. The third one to recall is to find if there is a slope which is suspicious. So if it is having an angle of maybe very high slope or steep rise, then you want to call it as an anomaly. So you have a threshold for that. You say that okay, if the slope is less than theta, then it's not an anomaly. Otherwise, it's an anomaly. So that's the hypothesis testing for that. However, we don't have beta 1 because this is the case when you have the exact value of beta 1, but we are estimating it. And estimation of beta 1 depends on the error. So you need to correct for the error. So we say that the null hypothesis, we reject the null hypothesis, which is it's not an anomaly. So we reject it if the estimate of beta 1 is between minus theta and plus theta, corrected by the error in the estimate. So this t distribution is used to correct that error. Finally, we go to the fourth one where we assume that not everything is a linear increase. So if it's not a linear steep, then your linear model will say it's failed. Now if it failed, it doesn't mean it's not an anomaly. It only means that the linear model didn't fit right. So what happens if the model is you have an exponential drive, or you need to fit a polynomial. So we can't have models for each and every one of these. So what we do is we have a quadratic model. So we take a polynomial of degree 2 and fit the data. Next, we see if the linear model fits better or the quadratic model. So for that, we use a coefficient of determination. So coefficient of determination simply looks to, it quantifies the point that your estimator, how much of data has your estimator grasped. So the higher the value, the better the fit. So if the quadratic coefficient of regression is greater than that obtained by least square, which is for a linear model, then we say it's an anomaly. So those are the 4 models. And we go to stage 2, and in stage 2 we want to detect scans and illegitimate TCP sequences. So I guess everyone knows about scans. It's very common these days to find out what services are running on which machines, and there are also ways to scan machines behind firewalls to know what is the amount of buffer the machines can tolerate, for example. So scans are quite useful to learn the system. But we go a bit beyond scans, and we want to know whether there are flows that do not conform to TCP's finite state machine. So TCP has this finite state machine based on which it responds to. So if it gets a SYN, it responds with a SYN ACK, and the client responds with an ACK, and then there is data exchange, then there's FIN, and we close with a FIN ACK, right? So that's a simplified version of what the FSM is. So what we're trying to do here is you have a small FSM running at the system, and see if the flow is conforming to the FSM or not. And the third stage is evidence correlation and decision making. So correlation can be made either in time or in space. So in time, if you want to make correlation, you're trying to say whether what you saw today, the anomaly that you saw today, or let's say in the morning, is related to yesterday's night's event, or an event 1 week back, and so on. So correlation is time is not really bounded, and it's kind of complicated because you need to have database as large and as efficient to compare with. The other possibility is you do correlation in space, which is you find out if the IP address that you that is related to the particular evidence has some other is occurring in some other events or evidences. So it can be the IP address in itself, it can be the network address of the machine, right? So yeah, we choose to do the space-based correlation here, and not time-based. Time-based we do, however, but over just a small interval of time. I think in 24 hours. Excuse me. So if you look at all the 4 techniques we mentioned, there are thresholds for each of them. To make it easy for anyone to use the system, we normalize the threshold to be in 0 and 1, and then put a conservative value to say what is low, medium, or you define what is low, medium, and a high score range. For example, anything beyond 0.75 is high, below 0.25 is low, and so on. The detection is eventually based on the number of evidences and scores. So it's not based on one single evidence, but multiple evidences, as well as the scores. Now, with the system explained, this is a recap of the framework. As we said, we first model the traffic, and we use these 3 features: interval time of flows, size of flows, and degree. And we detect anomalous patterns. These are the examples. We detect scans and TCP sequences, and finally correlate them to make a decision on whether a session is anomalous or not. Finally, we go to the performance evaluation. For the data, we took both benign and malicious traffic, close to 1,000 benign sessions and 1,400 malicious sessions. But the sessions are actually huge, because it depends on the time window that you are looking into, and therefore there are a few millions of flows in fact. The benign traffic was obtained from the ICC's dataset, that's from Canada, University in Canada, the MBNL dataset. That's quite old, however. And the third one is from two of the co-authors. So it's a little private, but anonymized, yeah. Anyway, we are not doing deep packet inspection, so we are looking only at the headers and time between packets. Malicious traffic was generated by malware, and this is obtained from the Stratosphere project, and the traffic is quite recent. There are a number of data sets. One of the data set we chose had these traffic from 11 different botnets. So we set conservative values for the threshold to test the system. We say if the output score is greater than 0.7, it's high, and the meta decision maker classifies a session as anomalous if at least 3 patterns or evidences are found with respect to a particular session, and at least 2 of them should have high scores, which means the third evidence need not have a high score, it just needs to stand out. So these histograms are for the different traffic sessions. On the left is the normal traffic sessions, and what we plot here on the x-axis is the number of evidences. So for the normal sessions, the left blue bar is for the number of sessions, and the right one is for the percentage. So if you look at this first one, you can see that the normal traffic session had no evidence for 60 sessions, but there were evidences in 1, and there were 20 of traffic sessions which had 2 evidences, and so on. If you look at malware traffic, almost more than 80% of them had 3 or more evidences. So the CDF of this is 84% and more. A couple of examples of the sessions detected. Here we see that the flow size in bytes at different time points is almost the same. So you can see a straight line fitting here. This is the model fit, and these are the data points. These are outliers, and this is detected using the linear fit model. The second example is the degree of the end host, and here you can see that the linear fit, okay, it's probably not so visible. I mean, it's not clear for our eyes, but with the model, the linear fit is not as good as the quadratic fit, and you can see the points are quite dispersed, but you would look at it suspiciously, so it's one simple way of knowing whether it's a linear model or not. In this particular scenario that I'm presenting, we obtained an accuracy of 82.6 with a false positivity of close to 8%. For a number of bots, we had high detection rates. There were few with low detection rates. They still had evidences, and they had at least 2 evidences. So it's a matter of configuring them to, if you want to detect evidences for the bots in the lower category of detection. I'll come to that later anyway. These are the results for the effectiveness of features. So this flow size in packets. So almost all detected sections had evidences on flow size in packets, flow size in bytes, interrupt time, and degree, but only half of them had related scans, for example. I guess most of them are scans, and very few of them are not scans, but still illegitimate TCP sessions. For the techniques, the outlier and the goodness of fit was useful in most of the evidences. Linear or quadratic models were useful in close to 8%. Again, that doesn't mean that the model is not good. It just detected some of them which were left out by the others. So if you want to change the decision criteria, for example, we tested with the criteria where you need only 2 or more evidences instead of 3 or more, and then the detection accuracy went up to close to 94, but of course the false positive also went down. We performed the computations on an Intel machine with 12 GB RAM, and we could achieve close to 3000 flows processing per second. However, it's still only an online solution. Of course, it works often as a forensic, but as I said in the beginning, in many of the network problems, there's a big overlap between forensic and security, and we would prefer to do it online and in real time, and real time is still a work in progress. Yeah. So to conclude, we developed this framework for gathering evidences to make sure that when you say there is an anomaly, there are a few evidences related to it. We actually have a prototype developed where the anomalies are shown, and then when you select them, you see all these evidences popping up as graphs. So an analyst would see these graphs coming up on screen, so it's kind of easier than going to the raw data, the log file, and finding out what happened. So we don't do any learning from the normal traffic. I think to be more correct, we also do not learn from attack traffic. We only observe, as in there's no machine learning of attack traffic pattern. It's mostly that we observe and know that these are the patterns that are most commonly seen, and therefore you model the patterns. In particular, if we know that these bots, for example, a set of bots has this set of patterns, then we could actually attach prior probability to those and have better results. But we didn't do that for this work. So it's still a conservative kind of system, I would say, because you could go a bit further and put more learning of the attack traffic, for example, if it's bots. But that's because we are not really focused on detecting bots. It's just a case study that we took for this work. Yeah. So the next steps, we want to enhance the solution on live real-time traffic, and this is challenging because you need to look at flows, look at traffic at the level of packets, flows, sessions, and compare it with those in the database. Also, we just use 3 features, and there are numerous more features that we can test with. This is again a continuation. Yeah, with this I come to the end of the talk, and we'll be happy to take questions.
So I think we've got time for maybe 2 quick questions.
Yeah. Hi. I see you used machine learning to find identify patterns. Did you consider using logistic regression or neural networks? Because it seems the patterns don't exactly match a linear regression.
So yeah, so we have another class of studies where we use explicitly machine learning, not regression, but classification from machine learning from the classification area. But that's a work that is ongoing, but for that we need huge amounts of data. So here we are not relying on data. We are relying on data only to evaluate. We are not relying on data to learn. So that is the context that we looked into. If we do not have that much of data to learn, what is the best we can do? Alright, yeah.
David, Olivia.
Okay. Could you go back to your slide where you have the robust calculation of the slope?
This one?
No. Yes, here. Okay, so you take, for the slope, it's estimated as a median of all slopes.
Yeah.
So taking the median brings a lot of robustness.
Yeah.
But may I suggest something that you might try, because I think you will calculate, when you're doing this, basically this is a quadratic problem, because so the complexity is quadratic, and you might introduce a lot of noise of ill-conditioned slopes, because points that are very close, basically they define slopes that are ill-conditioned. Mm-hmm. And intuitively you might have more trust in slopes where points are further away. So basically you could take kind of a windows, let's move along the set, and take slopes with pair of points, one of each side of this window. Mm-hmm. And this would reduce the time, because if you go real time, you might have a time issue. and you would eliminate all the slopes where the points are too close, which gives actually no information because the slope is very unstable.
Yes, that's a valid point. However, it's only the knife algorithm which takes quadratic. There are other algorithms for Thielsen which is faster than quadratic, so it's still not linear. Yeah, so it's n log, I think order of n log n or n root or something. Yeah.
All right. Thank you very much, Dinil. Let's give Dinil